All right, let's dive right into this explainer. What actually happens when our tried and true models of the universe suddenly hit a massive system-breaking bug? See, for the longest time, we thought we basically had the architecture of planetary systems completely figured out. We had a model, it worked perfectly for our local neighborhood, and we naturally just assumed it applied everywhere else. But as we've expanded our view deeper into the cosmos, we've encountered some truly impossible edge cases. So, what exactly do we do when the universe flat out fails our system validation test? For literal centuries, we thought we understood the precise manufacturing process of a solar system. We had the blueprint. But then, as our tech leveled up, the cosmos started feeding us data that completely rejected our build spec. I mean, we started finding planets in places where the laws of physics, at least as we understood them, said they absolutely could not exist. So consider this our cosmic system diagnostics report. We're going to trace exactly how these unexpected edge cases completely broke our models and how they forced us to rewrite the foundational code of planetary formation. Let's start by taking a quick look at what our original localized dataset actually looked like. Our original build spec was known as the nebular hypothesis. Formulated way back in the 18th century by guys like Kant and Laplace, it basically proposed that a rotating cloud of gas and dust collapses down to form a star, and all the leftover junk flattens into a disk. But here is the massive assumption they made. They believed planets form exactly in the spot where they currently reside. For the longest time, our own solar system was our only data point, which created this massive local bias. Earth is rocky and close to the sun, Jupiter is gas and far away, so we just assumed everything in the universe followed that exact same spatial logic. But to actually see past that local bias, we desperately needed better diagnostics to observe what was happening out in the wider galaxy. We couldn't exactly just peer through a standard telescope and see distant planets. We needed serious engineering precision. Enter our high-precision debugging tools, radio velocity and transit photometry. Radio velocity lets us detect the tiny gravitational wobble a planet induces on its host star, literally pulling it back and forth. Transit photometry, on the other hand, measures the incredibly minuscule dip in a star's light when a planet crosses right in front of it. These two methods acted as our cosmic magnifying glass, finally allowing us to measure distant systems. And in doing so, they totally expose the fatal flaws in our original logic. Which brings us to the very first major system crash, hot Jupiters. This is just a brilliant illustration of the impossible contrast between what our models predicted and the absolute chaotic reality we actually found. On one side, you have our normal solar system, rocky stuff close in, giant gas worlds safely in the freezing outer limits. But on the other side, chaos. We started finding exoplanets with the mass of Jupiter whipping around their parent stars so unbelievably close that they complete a full orbit in as few as 18 hours. 18 hours! That's their entire year. Finding these massive, gaseous behemoths so close to their host stars was this massive, unexpected input that just absolutely crashed our accepted formation models. According to the original build spec, it is physically impossible for a gas giant to form in an environment that intense. The scorching heat would instantly vaporize the ice and dust you need to build the planet's core, right? And the violent stellar winds from the young star would just blow away all the gas before a planet could even take shape. So finding a hot Jupiter was a total, critical failure of the nebular hypothesis. So how do you patch a bug that big? Astrophysicists had to introduce a brand new core technical concept. We call it planetary migration, because listen, if a hot Jupiter couldn't actually form right next to its star, well, it must have traveled there. We finally realized that planets don't necessarily stay where they're born. A giant planet's core forms way out in the deep freeze of a solar system, past the snow line, and pulls in a massive envelope of gas. But then, as it interacts with the surrounding disk of gas and dust, it actually alters its orbit. It starts drifting inward toward the star, almost like a ship caught in a really powerful ocean current. And depending on the environment, this migration patch can execute in a few distinct ways. You've got Type 1 for smaller planets surfing density waves, Type 2 where massive planets clear actual gaps in the disk. Then there's tidal and planetesimal migration, where gravity and rocky debris literally scatter planets into entirely new orbits. It's a dynamic, messy process. But hey, it was the fix we needed, and our models were updated. Okay, so we patched the models. We're good, right? Well, just when we thought we had it figured out, the universe threw the ultimate edge case at us. Welcome to the Neptunian desert. Because even with planetary migration, there are still rules. If a massive Jupiter-sized planet migrates close in, its sheer gravity can hold on to its gas. But if a mid-sized Neptune-like planet migrates too close, it enters this desert. It's an orbital kill zone so aggressive that intense stellar radiation should completely boil away the planet's gaseous atmosphere, leaving absolutely nothing but a shriveled-up rocky core. Finding a Neptune-sized gas planet in this zone should be strictly impossible. But then, enter NGTS-4b, completely appropriately nicknamed the Forbidden Planet. This exoplanet is residing right smack in the middle of the Neptunian desert, getting absolutely torched at 1,000 degrees Celsius. To put that into perspective, that is significantly hotter than the surface of Mercury at high noon. Finding this thing out there, with its gaseous atmosphere entirely intact, is just a stunning anomaly. Astronomers have literally compared it to finding a snowman in a blast furnace. It has no business being there. Its very survival forces us to, once again, completely rethink our models for atmospheric retention under lethal stellar radiation. Defying basically all logic, this Neptune-sized exoplanet maintains an incredibly tight orbit of just 1.34 days. It is just zipping around its host star at blinding speeds, getting constantly bombarded by a level of X-ray and UV radiation that frankly should have stripped it down to the bone millions of years ago. Ed Gillen, an astronomer out of Cambridge, really hit the nail on the head. He pointed out that this is the very first exoplanet of its kind found in this zone, proving the Neptunian desert isn't entirely dry after all. So how is it surviving? Well, researchers suspect it either migrated into this brutal neighborhood very, very recently, meaning the star just hasn't had time to evaporate the atmosphere yet, or it has some completely undiscovered chemical superpower protecting it. Which really brings us to our final takeaway about system validation on a cosmic scale. Think about it this way. A software engineer learns significantly more from a catastrophic system crash than from a totally successful run. A crash actually shows you where the limits of your architecture are, and it is the exact same for astrophysicists. We learn infinitely more from impossible planets like hot Jupiters and the Forbidden Planet than we do from the ones that behave nicely and fit our Earth-centric models. These forbidden planets are the ultimate edge cases. Their failure to meet our build spec is exactly what allows us to discover the true, highly dynamic architecture of the universe. Which leaves us with a pretty thrilling question. As we spin up even more powerful debugging tools like the James Webb Space Telescope, we really have to ask ourselves, what impossible bug are we going to find next? What new world is out there right now, just waiting to shatter the rules of physics as we know them? Keep looking up, because for sure, the universe is nowhere near done testing our models.